for this lesson, we're going to be talking about freefall and many things related to it, so including gravity, making assumptions, and then using some of the kinematic equations that you should have looked at in the last lesson. So when we talk about things in freefall, freefall really is just essentially when an object just has gravity working on it. So an object in freefall, the most standard case is you can imagine maybe there's like a cliff or something. There's a person up here, and they have a little ball and they drop it, and it goes downwards this way. Something you may have noticed when you drop something is that it gets faster and faster and faster. And a really easy way to tell that that happens is that when the ball is up here, it's not moving. So it has an initial velocity of 0. And yet, when it goes down here, or even after you let go of it, it's moving. So that means there's some type of acceleration. That means gravity accelerates objects toward itself. Something that we can do, though, just to keep in mind, is that we know that essentially the Earth is a circle. It's actually pretty spherical. I think there's a statistic like if you have a marble is less round than the Earth is. If you were to make a marble the size of the Earth, that marble would have more ridges. So yeah, no matter where you are on the Earth, an object is always going to fall towards the center. So something that we can do in physics, though, is we can always just assume that rather than having and worrying about things that are round, in our next chapter, things being round would make these problems a lot harder. We're just going to assume that anytime we do anything with gravity involved, that it's happening across a horizontal plane. So something dropping this way is going to be the same as something dropping over here. When we talk about gravity and how it accelerates things, gravity accelerates objects towards the Earth at a rate of, we're going to use 10 meters per second squared. Just to kind of remind you guys, remember, what that means is that if you have an object and it starts to fall, so you have this little object and it starts to fall, at t equals 0 seconds, its velocity is going to equal 0. At t equals 1 second, our velocity will equal just about 10 meters per second. At t equals 3, our velocity is going to equal 30 meters per second. And you can kind of see how that progresses. At t equals 100 seconds, our velocity would, hypothetically, if we could fall for that long, be 100 times 10, which is 1,000 meters per second, which is completely unrealistic. You're never going to really have to deal with a time that's this big, so don't worry too much about that. But I just want you to be able to see the general trend of how gravity accelerates things. The real value for gravity is technically 9.81 meters per second squared. There's a certain amount of precision that you can get if you want, but in this class, more often than not, we're just going to be using this 10 meters per second, and that should be good enough. And that's actually going to make calculations a lot easier. Something else to keep in mind is that when you are dropping things, it is very important to decide which way is your positive, which way is your negative. A lot of times we're going to want to make our direction of motion our positive direction. It's just going to make things a lot easier, so you don't have to worry so much about negatives happening. And so next thing that I kind of want to talk about is making assumptions. So for example, let's say we start with like the easiest type of free fall problem. So we'll have like an example. So we have a ball. It's some height up in the air, and it falls. Let's say it's going to fall for 3 seconds. It falls from, we'll say, rest. So I'm going to put this in parentheses. Falls from rest. And we want to answer how fast is it falling after 3 seconds. So the thing is, we're going to have to start using our kinematic equations, right? So just to kind of reiterate those, we have the kinematic equations. We have three main ones. So we have our v final equals our v initial plus at. We have our displacement, or our change in x, equals our initial velocity multiplied by our time plus 1/2 the acceleration multiplied by time squared. And our last one, v final squared equals v initial squared plus 2a multiplied by our displacement, our change in x. Don't be afraid again of these triangles. Always remember, triangle x can reduce down to our x final minus our x initial. Some other things, initial velocity just means your starting velocity. Final velocity means your ending velocity. And when you choose a starting and final point, remember that you are choosing it. So you could really choose any which way. So even though I give you a problem and I may say like, oh, it starts from rest and does this other thing, you can really change that problem to fit whatever you need to make it fit. So going back to our example, we basically always are going to need three variables in order to solve for a fourth one. And this is because if we look at all the kinematic equations, there's a common theme. We always have a change in x, or not we always have, but many times we have a change in x. We have a v final, we have a v initial, we have an acceleration, and we also have a time. And all of these equations have four variables that we can use. If we look at this one, we have v final, v initial, acceleration, and time. In this one right here, we have we don't have v final, we do have v initial, we do have acceleration, we have time, and we also have change in x. Not to be confused with this right here. So should be hope that's not misleading to you. And let me get this out of the way as well. For this last one, we have v final, we have v initial, we have acceleration, but this time we don't have time, and then we have a change in x. So you can see in every single one, we're kind of missing something somewhere. So in this first one, we're missing our change in x. All of them do have initial velocity, but you could always use systems of equations to solve for that if you're ever missing that. So that should never really be too much of a problem. So the idea basically is this. If I have three of these, so let's say I have v final, v initial, and acceleration, then I could solve for time. If I had change in x, v final, and acceleration, then I could solve for initial velocity. If you have three of these five variables, you can solve for the rest of them. You only ever need three. But when we look here, back to our example, we only have two. So the question becomes like, what do we do? Well, this is where we're going to talk about assumptions. So assumptions are just basically truths or variables or things that you can know just by knowing the setting or the context of the problem. So we'll say variables or helpful truths that we know because of the context of the problem. And so for our example, you can usually assume this is going to happen on Earth, and that most of the problems are going to be realistic. So something that we can assume from our problem is that if we're on Earth, then we know our acceleration. Our acceleration is just going to be gravity, is g. Anytime you see g in a problem, it most likely will represent gravity unless otherwise specified. G is also different from big G. Big G we'll talk about much later. And so if we know acceleration, it's 10 meters per second squared, that gives us some of the variables that we need. But oh wait, technically speaking, we're still missing one more. The other one that we can also assume is our v initial. If it starts from rest, that means our initial velocity is 0. So what we're going to do is we're going to look at what we got. We got initial velocity, acceleration, and time. And we're going to look at which of these three equations has those three plus our v final. So first of all, if it doesn't have vFinal, we can't use it. So we're definitely not going to use this one. So it has to be one of the other two. Our first one has initial velocity, acceleration, and time, and that looks pretty good. So we're going to use number 1. So I'm going to solve that down here. So let's rewrite all the variables we actually have. So we're looking for vFinal. We have v initial, which is 0. We have acceleration, which is 10 meters per second squared. And we have our time, which is 3 seconds. Next, I'm going to want to write my equation out. vFinal equals v initial plus acceleration times time. And I'm going to want to solve, make sure the variable that I want to solve for is by itself, and vFinal is already by itself, so that's nice. Then I can start plugging things in. Well, we know that our initial velocity is 0, so that just kind of cancels out, plus our acceleration multiplied by our time, which is 3 seconds. Something that I want to take time out to note is that this x can kind of be confusing, so a lot of times I'll use a dot. So I'm actually going to change that right now. Whenever you see this dot, it just means we're doing multiplication. So we have 10 times 3. Well, what's 10 times 3? That's easy. It's 30 meters per second. So after 3 seconds, our ball is falling with a velocity of 30 meters per second. So pretty easy. There's a lot of other things to kind of keep in mind. For example, this acceleration right here is positive. That means that my gravity, it is a vector. Acceleration is a vector, don't forget about that. So I denoted my downwards as positive. So let's do a couple more problems to kind of like understand kind of what's going on and get you comfortable with using these. Another problem that we could have, for example, is when a ball gets thrown up, or an object gets thrown up, and it comes straight back down. Now, it's really hard for me to draw straight back down, so I'm going to kind of draw it just like that, right? So it goes up, comes back down, lands exactly in the same spot that it started at. My question might be, how high does the ball get thrown up? Right? How high does the ball get thrown up? And this is going to be a little bit tricky, but it's actually not too bad. So first thing we want to do is kind of write down what we have. Let's say the ball has a hang time, so it's in the air for a total of, let's say, 4 seconds. 4 seconds. And I think, yeah, we're just going to use that. We're going to say, so as the ball travels up and down, it's in the air for 4 seconds. And you might just be like, wait, we just have 1? Well, let's use some of the assumptions that we have. First of all, let's look at, is this on Earth? If it is, sweet. The only thing that's going to be changing its velocity, so its acceleration, is gravity. So we got that too, 10 meters per second squared, but we don't know if it's plus or minus yet because we haven't denoted that yet. We're looking for distance, so we know we're looking for displacement. But now we still need one more variable. And so we don't have, for example, if we call it, we're going to call this bottom point. We're going to call that point A. We're going to call this top point. You're going to see why it's important later. Point B. We're going to call this bottom point right here, point C. So with these 3 points, we don't know the velocity here or here. Something that we do know is the velocity at point A equals the velocity at point B, or at point C, which actually isn't too helpful for us. If we were to calculate the displacement of a ball that goes up and comes back down, right? Really quickly, that displacement is 0. So from A to C, our displacement is 0. What we really actually want to find, if I'm asking you for our change in x, what is the height the ball reaches? Or what is the highest point the ball reaches? We're actually solving for a completely different problem. We're either solving for a ball that goes up and it gets to its maximum height point, or we could be solving for a ball that comes down and lands at our ground point. Because if we were to measure and find the displacement of from here to here, which this would be our change in x from A to B, and this one would be our change in x from B to C. If we find a displacement of that, that would actually give us how high the ball went. So what we're going to do is we're actually going to do both of these problems. So we're going to choose our directions and we're going to keep them constant for the whole time. So just for the sake of doing it, I'm going to choose positive as my upwards, negative as my downwards. And we're going to see what happens. So first, we're going to be solving for the change in x. So we'll kind of have this right here. We'll call this the first one situation 1, and we'll call the second one situation 2. So we have situation 1. A ball goes up to its highest point. So something that is very nice is, well, first we have some of our assumptions already. T is not going to be 4 seconds now. The time from A to B is actually just going to be half our hang time. So it's actually going to be 2 seconds. Gravity, still a solid 10 meters per second. However, if upwards is positive and downwards is negative, gravity always points down towards the earth. So our gravity is actually negative. So we'll see how that plays out. Something else that we need to know, or that we can assume, is the velocity at the peak, the velocity at that highest point. If you notice, when a ball goes up, right, let's say this starts with a velocity, and this is hypothetical, it's not the actual problem. If a velocity starts, let's say, with 20 meters per second of velocity, or the ball starts with that much, eventually, right, as it comes up here, right, once it reaches its highest point, that's where its velocity is going to be 0, because then eventually when it starts coming back down, our velocity down here is actually going to be a negative 20 meters per second. So actually, I guess in a way, right here, I kind of lied. It's not your velocity of A equals velocity of B, it's velocity of A equals the negative of velocity C. So same amount, same magnitude, opposite direction. But what this means, though, is since we've changed the problem, let's call this A, call this B, this initial velocity right here is actually not too important. What we can use here is our final velocity. So we say a V final equals 0. So that's nice. And then we're looking for a change in x from point A to point B. So we have these 4. And what we're going to want to do is look for which one has all of these. So we have x, V final, G, and T. So we go back to our equations, x, V final, G, and T. Well, it actually kind of looks like none of those fit the bill, right? None of those fit the bill. And so what we're actually going to have to do is essentially a systems of equations problem. And that's actually really, it's not too complicated mathematically, but it's more than I want to take you guys through. So this is the issue that we run into with this one. Is that we don't have enough of the variables to solve for them. If you really want to do systems of equations, all you're really going to have to do is get 2 of the equations that have your V initial, so really any one of these, and then kind of cancel that out so that your V final is kind of left over. But let's try situation 2 now. Let's see what happens there. So now we're solving for a ball that goes down, which is our bottom point. Time is still 2 seconds. From now we're doing B to C. Gravity, still negative 10 meters per second squared. Our V initial now, right, because we're doing a different problem now, we're going down from B to C, so our V initial is 0. And our change in x is, we don't know, but something to keep in mind is if we're measuring from here to here, our change in x should be a negative number. B to C. And what's nice is that we do have an equation that fits the bill. So we have change in x from B to C is equal to our initial velocity multiplied by our time plus 1/2 AT squared. Something that immediately you should see is that this just cancels out because our initial velocity is 0. And then we get 1/2 multiplied by 10 meters per second squared multiplied by our time, which is just 2 squared. 2 squared, remember, just because we have both of these. And this is actually a fairly easy problem. We get 40 in here, and we're taking 1/2 of 40, so we get a change in x of 20. But hopefully you noticed my mistake, which was the negative right here. right? So this is actually a negative 40. And we get a negative 20 meters. So when we go back to the question, what is the highest point the ball reaches? We need to answer the question within that context. If we say that the ball reaches a negative 20 meters, then we're actually answering kind of like this question. So if we went here and here, right, negative 20 meters from the question's perspective is actually maybe somewhere down here, right? But what we also know is that the displacement from point B to point C is 20 meters, so we can simply say that they're related, they're basically the same. So our final answer is going to be 20 meters. So that's kind of how those work. Sometimes you want to set up a problem in a certain way so that things just become easier. If you notice with both of these, they were actually the same variables. Just one of them was a final and we just didn't have an equation that actually worked for that. But you could create that if you wanted to. You just have to use systems of equations. So just some other problems to keep in mind. You may have a problem that, for example, maybe a ball comes up and then it comes back down and it goes past its point, right? So if it goes past the point that it started at, we can't assume, if this is A and this is B, that the velocity of A equals the velocity of B. You can only assume that it's on a flat surface. Another question that you might have to answer is maybe a ball gets thrown up and it doesn't come all the way back down. In that same way, you can't assume your velocity of A is going to be equal to your velocity of B. Right? But, and some things that you have to be careful about too is that you can't cut the time in half for those either if you need to. Remember that we had to, and that we could cut the time in half because this traveled straight up, straight back down, landed at the exact same displacement. But don't worry too much. If you get one of these problems, I pretty much have to give you a way to solve for it. And I don't want to use specifically too much math. I do want you guys to just kind of like understand and be able to solve for essentially a ball dropping. And so if you can do that, you should be in pretty good shape. Specifically a ball dropping from rest. So that's all I have for you guys today. I know today was a little bit of a long one, but it's very important that all of you are able to make assumptions, correct and good assumptions, so that these problems actually become a lot more easier. So don't forget about your directions, choosing positive and negative, things like that. And don't also forget that gravity for us is going to be 10 meters per second squared, but it could technically be a plus or minus depending on your direction. So that's all I have for you guys today. Have a good one.